Okay, so last time we were talking about triple integrals. Recall that the sort of the motivating example is if you have a three-dimensional solid region, right? And on that three-dimensional solid region, you want to do some sort of a chop it up, add it up. Okay, so. So the big idea is you chop it up into little pieces, and then on each little piece you can make an easy argument, such as if you know mass per unit volume, then you can multiply by the volume of that little piece, and that tells you mass, and then you add up all the little pieces of mass. Okay, so I'll remind you, and again I gave a whole speech about this last time, but this point of view where you're just looking at the domain, right? And then you're realizing that you are chopping up the domain. That's what the Riemann sum is actually doing, is chopping up the domain into little pieces. And then on those little pieces, you're doing a calculation, right? This is ultimately a pretty natural point of view, and it's accessible. We can actually draw pictures such as they are, right? By contrast, if you try to visualize this as, we're going to look at the graph of f and figure out how much of whatever you would call that is underneath that graph, whatever that means, right? Then you would find yourself looking at a four-dimensional picture, and this is not accessible. So you can't make any sense out of that, and so it's really not a good point of view on how to understand triple integrals. So with that in mind, again, I encourage that you likewise think about this, I'm going to loosely call this the domain point of view on single and double integrals as well, right? To set up a nice pattern, have a consistent apples and apples comparison between these three different things, as opposed to, again, it's a common choice to think of single variable integrals this way, double integrals this way, and then triple integrals this way. And this leads to confusion and confusion. Let's just leave it at that. Okay. All right, so moving along. When we were doing double integrals, one of the first observations that we made was that they can be computed with iterated integrals. And same true for triple integrals. Triple integrals can be computed with any of 6 different kinds of, orders of differentials on iterated integrals that you might want to compute. Of course, if you have 3 differentials, and you can put them in any order you want, right, then, there's 6 options there. Good news. Same result. Triple integrals are iterated integrals, or let's say triple integrals can be computed with iterated integrals exactly analogously to the similar statement for double integrals. The bad news is I can't give you a geometric argument for this. You may recall that the way we made this argument for double integrals relied on this picture. Right, interpreting double integrals as representing volume under a graph, and of course I don't have that picture accessible, so that's kind of off the table. Good news, this isn't really a course about proofs so much, so I'm going to assert that this is true. I'm going to appeal to your sense of pattern and willingness to trust me, and claim and leave it at that, that this works. Okay, so altogether, again, we've defined a bunch of things, and here's our roadmap for making arguments that involve triple integrals. You'll notice that this is laid out on the page practically identically to the same diagram, the analogous diagram we had for double integrals. So if you want to solve an application problem, whatever that application may be, step 1 will be to turn it into a triple integral. Step 2 will be to rewrite that triple integral as an iterated integral. And then step 3 will be to compute that iterated integral by cranking it out with the fundamental theorem. Okay. All right. Now, what you can't do, and again, I want to emphasize what is not a reasonable argument. Again, the analogy is perfect with double integrals. You can't argue, for example, that mass is some geometric quantity related to the graph of your integrand for a couple of reasons. First of all, I can't draw that graph. I don't have any intuition for what that would look like because I'm a three-dimensional critter and this would require a four-dimensional picture and it just doesn't make any sense. And even if you could, in what sense is mass a four-dimensional thing? Right? It doesn't hold water as an argument. So don't try to do this. That doesn't make any sense. And likewise, don't try to turn, again, for example, mass directly into an iterated integral. That also doesn't really make sense. The very first thing that you have to do when computing such a thing, you would have to argue that inside the iterated integral, mass per unit volume times length means something. And you can probably come up with some sense for what that ought to mean, but the point is it's not a pre-existing concept. It's not... it's just not feasible, right, to make such arguments every single time you want to compute something. Okay, so always this path, and always you're going to give me all three steps. Okay. All right, so for example, suppose you want to compute the mass sitting inside of this rectangular box, where mass per unit volume is given by this formula. Okay, step one. Mass is a triple integral. Mass per unit volume times volume gives you mass. Chop it up, add it up. Whole is the sum of the parts. Say it however you like, right? There's that first step. Second step, we rewrite the triple integral as an iterated integral. Notice that the range of values of x on the box gives me my bounds for my x integral, wherever it is in the order of your differentials. Range of values for y gives you the y bounds, and the range of values for z gives you the z bounds. So easy to write that down. All right, and then lastly, the plug and chug of it all. And again, we have the same issue with keeping track of which variables are playing what role at which stage of the calculation. Notice in the computation of this inside integral that we have to start with in doing computation, for the purposes of this inside integral, don't forget x and y are constants. So we treat x and y like constants. And as such, they just are like any other constant factors that come along for the ride. And this first antiderivative that I do here, where I take the antiderivative of, 2z, the constant is, again, just along for the ride as usual. The antiderivative of 2z with respect to z is z squared. Is everybody happy? All right. Okay, and then everything else is analogous to double integrals. Again, strategically, I advise you to indicate when you're about to plug in your bounds, indicate specifically which variable you're plugging in for. This will avoid accidental oopsing, plugging them in for the wrong variable, perhaps in addition to the right variable. It's easy to mess that up. Okay, so next, a sort of analogous extension. What if we have non-rectangular domains? How does this change things? Well, again, you may recall, with double integrals, I made a geometric argument. It involves the use of the graph. It remains that for triple integrals, I've got too many variables, I can't draw the graph, so I can't show you that argument. I'm again going to just assert that the process is totally analogous. So here's, just to have it down on paper, here is that analogous process. And let's see, I'm going to zoom out so I can fit all this on the page. We're going to go through a 3-step process, once for each of our variables as we develop our integral. And then repeat as I go to the next variable. So step 1, you'll notice from the picture here, I'm starting off by slicing in the x direction. You'll see from the iterated integral I'm developing, I've got dx on the outside. Arbitrary, doesn't matter, this is just an example. But doing my X slicing first. Here's what an X slice looks like. Right? That's in a plane perpendicular to the x-axis. And that's what they look like. So you've got to first identify what do these things look like. Then figure out where's the first and last of them. And I think you can see that here, for that value of x, is where the first x slice is. And then way over here is where the last x slice is. Just looking at the picture. And that gives you your bounds for that coordinate integral and the iterated integral you're developing. And once you have those bounds, you then fix a slice. So a generic slice fix that generic slice and then move back to the beginning and repeat the whole process now this next time for the next variable arbitrarily. Doesn't matter. Here arbitrarily I'm going to do y next. Notice that my y slicing is the second slicing I'm going to do. So again, what do these slices look like? Slicing perpendicular to the coordinate axis. Those slices, let's see here, perpendicular to the y-axis. And slicing, not the whole solid, but slicing just my existing x slice. I get a little line segment looking thing like this. Right? Let's ask then on the entire x slice, where's the first and last? Well, first slice there, last slice there. First and last gives me my bounds for my y integral. Note they're going to depend on x, right? The first and last values of y on this slice, specifically this being a slice that happens at a particular selected value of x. Well, if you move x, then this slice here will be moving in and out and will change the shape of that slice, and of course then the y bounds that came from that slice will also change. So, as we would expect then, these y bounds are functions of x. Right? They depend on x. Okay. We then fix a value of that variable. So we're going to have, going forward then, not only is x fixed, but now y fixed. We've got our x slicing done, we've got our y slicing done, and now we focus our attention on that y slice. I emphasize it's the y slice of the existing x slice. Right? And then now we move on to the next variable. What do z slices look like? Well, they're just points. Where do they start? Well, here's the first z slice, which gives me my lower z bound. Here's my last z slice. It gives me my upper z bound. And then I'm done. Right, so in some sense, it's the exact same process as with double integrals. It's just that I go 3 times. I don't think I did that right. Let me try that again. 1, 2, 3 times through this process instead of just 2 times through this process when we did double integrals. So, yeah, 3-dimensional instead of 2. Expect a few differences like this. But other than that, it's the same pattern. Okay. Couple of observations to make. Again, we're constructing the integral from the outside in, just like with double integrals. That's very important. You have to start with your slicing on the outside and then work your way in. Secondly, notice that each bound, such as these inside bounds, right, are functions of the variables further to the outside. So you see here, in this case, x and y, The z bounds are functions of x and y because x and y are further to the outside from the z integral for which those are bounds. Right? Said differently, variables further to the outside for a given integral are treated as constants. Same statement, different language. Okay, and then lastly, in this next one, we will see mostly by example. The way we're going to get bounds is we're going to identify which points on the domain they come from. Those points will be on certain surfaces that we can identify from the picture, which will have certain equations that we can either identify from the given statement of the question or infer from other things that are given. But same pattern, bounds come from points which are identified on surfaces that have certain equations. And then you solve for what you need. Just like with double integrals. Let's dive in and do an example. Tetrahedron. Here we go. This tetrahedron is defined by these four planes that are given in the statement of the question. Flashbacks to chapter 1, right, where we saw equations of planes. Given these four planes and thus this tetrahedron, how would I compute a triple integral? More to the point, how would I turn this triple integral into, eventually, we're going to go through all these details, how would I turn this triple integral into this iterated integral? And let me remind you, again, what that means is that we're only doing just this part of the process. I just want to focus on how to turn triple integrals into iterated integrals. Let's not worry where this triple integral came from. It came from some application, whatever. Right, let's assume we already have the triple integral. And then furthermore, what am I going to do with the iterated integral? Well, of course you can compute it. And again, we've already talked about how that goes down and not what I want to focus on right now. So we're focusing on just phase 2. Okay, so you have 6 choices of how to slice it. Try not to slice through corners. Try to think in terms of what I prefer to think of as a function of what, so that you don't find yourself accidentally solving for the wrong thing and having to introduce square roots unnecessarily or arc cosines or something nasty like that, right? General, same guidance as with double integrals. Notice in this case, that's pretty symmetric. Doesn't really matter, whatever you slice, so whatever. Arbitrarily then, I'm going to start with x slicing. Here's what x slices look like. Here's the first one. Here's the last one. And, look, in this case, it's pretty straightforward where this first slice comes from. This first slice is clearly, from the picture, clearly in the YZ plane, aka the plane where x equals 0. And that means that the x bound is x equals 0. Because it's in the plane x equals 0. Sometimes the fish jump in the boat. All right? Everybody happy with that? Questions, feel free. All right, this last one, though, where do I get this upper bound? How do I know the upper bound is x equals 1? Well, here's the point in question. And there's 3 things that I can write down about this point in order to understand, where it is and thus what the value of x is. Notice, this point is on that surface, which has that equation. That's just an observation from the picture. You gotta have a picture to make this realization that that's where that point is. Picture is essential. Let's see here. Next, what else do I know? Well, it's clearly on that plane with that equation. Again, thank you, picture. Couldn't know that without the picture. Right? Keep in mind, I emphasize, it's not about whether you get the right answer. It's about whether you have communicated a valid line of reasoning. And without a picture, I don't know how you'd make the obvious case that the last value of x, of course, should be on this plane. Not clear where that would come from. So make sure you've got a good picture. Okay, lastly, this blue point is also on that plane with that equation. Again, this is a consequence of looking at our picture. That's how we know that that point is there. So, reminding ourselves what we're doing here. We're trying to find an x bound. So, this point here, about which I know all of this information, is going to tell me about a value of x. So in this trio of equations, I need to solve for x. And there's a little bit of work to be done there, not that bad, and x is 1. And thus this upper bound is 1. Everybody see the process? Okay, so just again, from a strategic point of view, let's remember, bounds are defined by specific points you can identify on your picture. Those points will visibly be on certain surfaces. Those surfaces will have certain equations. Solve for the variable that you want. All right, proceeding along. Per the pattern, we're now going to fix a value of x. X will be fixed. We're going to therefore look only on this x slice. On that x slice, I now want to ask what is the range of values of y. Okay, well, y slices look kind of like this. All right, where's the first and last? First slice is there. That's clearly in the xz plane where y equals 0. No extra work needed. I can just assert. It's pretty obvious from the picture. That's where y equals 0. Let's see here. The last slice, again, at a point like that. Now, again, I have kind of a problem. That's is not clear exactly where that point is. I need to understand what I can say it now about that point. That's going to define my y bound, my upper bound. And notice I have 3 things I can say about it. First of all, I know what x is. X has been fixed. Well, let's not lose track of that. I like to write that down by saying x equals x. I know it's a silly kind of way to represent it, but I find that somehow satisfying reminder that my answer is allowed to be in terms of x. It's a recognition that x is known. There. Okay, so I'm on that x plane, you might say. What else do I know about this point? Well, the picture tells me it's on that plane which has that equation. Gotta love the picture. The picture also tells me, let's see, that it is on that plane with that equation. Thank you, picture. Can't do this without the picture. Everybody good? So, again, what am I doing here? I'm trying to understand this point so that I can find my upper bound for y. So in this trio of equations, I need to solve for y. And you get 1 minus x, which then is my upper y bound. What do you think? Is everybody happy? All right. Now, before I go on to the next one, let me just point out, I'm hitting this really hard, I know, but gosh, it's so important that the picture tell us what's going on. Notice the point in question here. It's not on that plane. Right? So how do I know not to include, for example, that plane, that equation, y equals 0, in the algebra that leads me to my y bound? Well, because the picture shows me that the point in question is simply not on that plane. Right? So I don't include that plane because the point's not on it. The picture is what allows me to draw that conclusion. Okay. All right. Now moving along. And again, with the understanding that x is fixed. We're on our x slice. And furthermore, that y now fixed. We are on then this y slice of our x slice. On that, what is the range of values of z? Okay, well, it starts at this point right here, which is in the plane z equals 0. And that's all I really need to know about it. If I want to know the value of z and it's in the plane z equals 0, then the answer is 0. So no problem there. Again, sometimes they're just immediate. The non-trivial one, this upper bound for z, what can I say about that? Well, let's not lose sight of the fact that I already know x and I already know y. Again, they've already been fixed as part of the outside integrals that we're using to develop here. And let's see, what else do I know about this point, aside from the fact that I know x and y already? And again, thank you, picture, which I forgot to erase that. That point is on that plane with that equation. The picture is what tells me that. And so again, I have equations in which I'm trying to solve now for z, and solving for z, I get that, and thus this. Everybody with? Okay. All right. Cool. Moving along. You do have 6 different orders to choose from, so that's good news or bad news, depending on how you look at it. It is a lot of options. Cool. We have flexibility. That's nice. Bad news. You do have to make a good choice, which means you've got a bunch of options to choose between and therefore arguably more to think about. So good news, bad news. Yeah. It remains, just like with double integrals, try not to slice through corners. Bad things happen. Morally equivalent reasons. So in the process of slicing, you don't want to mid-process slice through a corner or an edge or something like that. Also, think about what you're going to have to solve for as a function of what. Right? If you find yourself with one of the variables being, polynomial function of the other variable, weird polynomial, you might not want to have to solve for those other variables. You might end up with a cube root or square root even, just as bad. So all else being equal, whatever is already, or what you would prefer to view as a function of the other variables, put that on the inside. If you can, all else being equal. Lastly, there's an observation here about projections, and the best way I think to explain these points about projections is first for me to get right into an example, and then I will come back as we go through this next example and explain what I mean by these points as we go through the example. So here we go. Here it is. We're going to look at this weird-looking region bounded by, well, first z equals 1 is that plane. And then I have this paraboloid, z is x squared plus y squared, and that gives me something kind of like this. I mean, it came out of, arguably, this whole great big paraboloid, but notice that the question says I'm looking for the part that's in the first octant, and thus I want just this part there. Everybody good with the picture? Okay. All right. Yeah. All right. So there's our solid. Let's try to make a decision on how to slice this up. First thing that we notice, z very naturally, very preferably viewed as a function of x and y. I mean, I could, I suppose, solve for x. I'm going to have weird square roots, and I don't want that. And likewise, I don't want to have to solve for y. So since I'm going to eventually have to solve for something, all else being equal, I'd rather solve for z because it's already done and it doesn't have any square roots in it. So that's an argument for putting dz on the inside in our order of differentials. Everybody with me? All right. Okay, let's talk about the projection business. I claim that there's a good projection into the XY plane. What do I mean by that? And let's start it slow. What do I mean by a projection into the XY plane? Well, I mean kind of hopefully exactly what you think. Namely, everything just gets pushed straight down into the XY plane. Just to generalize, everything gets pushed perpendicularly to the XY plane. into the XY plane. And so the projection itself, what I'm claiming is a good projection, is just, well, this quarter disc. I claim this is a good projection. So now let me walk you through what I claim is good about this projection. First of all, the shape itself, not bad. The actual shadow here. This is a reasonably desirable shadow. Sure, it has one curved edge on it. What are you going to do? You can't always require that you deal only with polygons, right? Sometimes you're going to have to deal with a curve, and this one, all else being equal, could be worse. Okay. The next thing. The top and bottom surfaces are nice. Let me explain what I mean by top and bottom surfaces. When I'm looking on this shadow, if I pick a point inside of that shadow, if I look at the part of the solid that is directly above that that point in the shadow, right? So picking a point down here in the shadow, looking at what is directly above it. First, let's talk about the bottom point of that interval. And I appeal to your intuition from the picture here. No matter where I am in this shadow down here, wherever this yellow point is down here, this bottom point will always be on the same surface. It's always on z equals x squared plus y squared. That's nice. So this is what I mean by the consistency of the bottom surface. And then now let's look at the top point. The top point up here is consistently always on that surface. Again, same equation all the way everywhere across the shadow. Right. So this is what I mean by a nice top and bottom surfaces. The top and bottom surfaces, same equation everywhere for the whole shadow. And nothing weird happened. I didn't get any inverse hyperbolic cosecants. I didn't get any, nothing, no nightmares arose. Yeah. How we doing? Is everybody with me? Okay, now, with that noted, let me explain why it's good. Like, what is the good news here? And the short answer to that question is that this shadow is going to give us a very convenient hack, shortcut, however you want to say it, for understanding the slicing process of the original solid. And it goes like this. Let's slice up our solid arbitrarily just in the y direction, just because that's how I have the picture drawn, whatever. The first slice in the y direction is that. Now let me ask the same question. What is the first slice if I were slicing up the shadow instead? Well, it's immediately below the first slice of the solid. They have the same y-coordinate because this is immediately below that. So, said differently, the starting value of y on the shadow tells you the starting value of y on the solid. Likewise, the ending value of y on the solid and the ending value of y on the shadow. Again, same value of y, because again, this is directly above that, and thus same y-coordinate. And then furthermore, once you've fixed y and are thus looking at just a single y slice on the solid, or at the same time, a single y slice of your shadow. Let's think now about how x varies. Right? Well, the first x coordinate, the first x slice on my solid is that. Whoops, I missed the thing. On the shadow is this. And again, same x coordinate because this is directly above that. So I can use the bounds on my shadow to understand the bounds on my solid, and likewise on the let's see, on the last x slice there versus there, again, same x coordinate. So this is a really powerful result. I don't have to slice up my solid. Notice how hard it is, by the way, to draw those slices on my solid. It's a tough draw. There's some weird stuff going on in drawing this. And good news, don't even have to worry about it all that much because the shadow, much easier to draw, tells everything you need to know about your x and y bounds. Much easier art problem, if nothing else. Everybody see the end there? So, having already decided that we're going to do this slicing in this order right here, specifically with dx and dy on the outside, I don't need to look at the solid. I can just look down here at this shadow. This shadow is super easy. It's just a quarter disc. Easy analysis that you can do over here. It's double integral-esque analysis there. And that tells you your x and y bounds. And we're 2/3 of the way with our iterated integral, and our picture has consisted of, well, really not that much, just looking at this shadow down here. Everybody see how nice that is? Okay, cool. The last thing I got to do is I do have to figure out my z-bounds. My z-bounds are going to come from looking at given a fixed x and y, looking then at I guess this would be an x slice of a y slice. I mean, we didn't actually draw it that way, and we don't have to have drawn this y cross section. But anyway, that's what a slice of a slice looks like, and I just need to know now, to get this lower z bound, I just need to understand this point, that purple point. Again, as previously noticed, it's always on this surface, which has a consistent and convenient equation. Z is x squared plus y squared, so solve for z in that equation. And it's x squared plus y squared. Right? And then analogously, finding the upper bound up here. The upper bound comes from this point. That point is on this surface, which again has an easy, consistent equation. It's always the same surface for all values of x and y, and z equals 1, and so that is our upper bound. Okay, so all together you see what I mean by, I hope you see what I mean by a good projection into the xy plane, and why we need it to be what I claim we need it to be. We want the projection to be nice so that this blue argument down here, our blue, bounds for x and y integrals, I want those to be reasonably convenient to write down. And then I need the consistent bottom and top surfaces so that I can have these bounds work out easily also. Everybody happy? Okay, I'm a huge fan of this trick. I think it's a very powerful trick. Real quick before I go on, I did want to make a pitch for something. Y'all have heard me say this before. I think this can't really be overstated. This picture is pretty hard to draw. If you don't believe me, give it a try. It's tough. If you want it to look really right. Notice how much, in order to answer a question like this, it is really helpful to have a good picture, right? And if you're making slicing type arguments, you have to have a good picture, or at least a reasonably representative picture. So being able to draw good pictures, very, very important skill to have, just, in this course really as a whole. So I'm going to remind you, pitch, I have that video available, 2 videos actually, miscellaneous topics playlist on my YouTube channel. Give it a look. I hope you'll find that useful. Just for the specifics, in one of those recordings, I go through this specific picture and all of the little subtle considerations and details that went into making this, I'm going to say, reasonably good end result drawing here. So if you want to know every single thing that went through my mind as I was drawing this, that's where it is. Okay. Alrighty, let's do the unit ball here. Okay, and again, we're going to presume a triple integral. Don't worry about what application this came from, whatever. We're just focusing on phase 2. We're going to turn it into, hopefully, an iterated integral. Arbitrarily, I'm choosing my slicing in this order. Doesn't matter. Kind of pulled one out of a hat here, dy, dz, dx, whatever. All right. So, how to think about this. 2 different points of view. You can slice, and then slice the slice, and then slice the slice of the slice. You can go through and do, in other words, an argument kind of like this one. It's a very healthy exercise. I encourage everybody to do that for this unit ball. The pictures are hard to draw, harder than you would think. But ultimately, like I say, it's a healthy exercise. So I hope you'll give that a try. I'm going to show you an easier way to do it, which is not to slice the slice, but rather to look at a projection. And again, you have options on where to project, and I claim that this is a good projection into the XZ plane. I'm just switching it up. Right, we could have done the XY plane, but we've already done one of those. So I'm going to project into the XZ plane, and now it's art challenge time. And can I pull this off? Yeah, close enough. So we're going to look in this projection of our unit ball into the XZ plane. Is everybody good? Notice the shadow itself, right? The actual shadow in the XZ plane. It's a disk. It's not that bad. No big deal. Because it's a disk, specifically the unit disk, basically double integral arguments will give us these bounds for our z and x integrals. We're 2/3 of the way there. Pretty sweet. Let's see, where's my lower bound going to come from? Well, I need to look in the y direction now. And in the y direction, well, I'll do it like this. In the y direction, notice the lower bound is always going to come from the, let's see, I guess you might call that the left hemisphere, right? And solve for y on that, on that left hemisphere, and you'll get this as the lower bound. And then the upper bound always comes from that hemisphere. Again, solve for y, and you get this as your upper bound. And I think that was a much easier argument than trying to draw the slices and keep track of, oh my gosh, I don't know, this is part of the slicing of the slicing of the slicing process. And you see it gets a little sort of hard to visualize. Okay. Much easier to think about a projection, lower and upper values of surfaces, and boom. Yeah?
This was a sphere where it was like non-uniform mass.
That's right. So the density, mass per unit volume, or whatever is your integrand. Maybe you're computing how many flies are flying around in here. Yeah, your density or what have you is just F, and it doesn't play into the domain at all. That's right. So this is a general fact, by the way. When you turn a triple integral or double integral into an iterated integral, the integrands are always the same. It's just about the domain, in other words. And the integrand just comes along for the ride. Everybody good? Okay, next example. This is a toughie. I'm going to show you the trick that turns this very, very tough problem into not that bad. We actually foreshadowed this, whether we realized it or not, back in chapter 1 when we observed that if you have an equation that doesn't have any y's in it, the result is parallel to the y-axis. Y'all remember that fact? It was way back in chapter 1. I only discussed that fact in relation to planes. But it's also a true fact in general about any surface, and there's different ways that you can think about that. There's, for example, an argument you can make concerning gradients. I'm going to leave that as a challenge question. If you're curious, how would you draw this conclusion by making an argument relating to gradients? And I'll give you another hint. It involves level sets. So anyway, something to think about. If you want more discussion of why this is true, come to my office hours. I'll be very happy to flesh that out for you. Anyway, check it out. We've got 3 equations that fit the bill. I've got 3 equations there that, they're planes parallel to the y-axis. And that gives me a tremendous convenience because this is no longer, arbitrary, random, 5 random planes. That would be very difficult to see how they intersect with each other and which ones intersect. And there's lots of kinds of surfaces that have 5 faces, right? So that would be very hard in general. But in this case, I see 3 of my planes are they're parallel to the y-axis, and so I'm going to have, you can see I've already kind of started drawing in here that we've got kind of a prism going on here. And I just kind of have details left over as to how far does that prism extend to the right, how far does it extend to the left. Everybody with me? Great foot in the door. Here's a strategic observation. Y'all hopefully willing to believe that I'm not going to give you any questions on the exam that are simply not tractable, right? And so if you find that on the exam or something like that, that there's some long list of equations that you've got to figure out what that bounds, there must be a foot in the door somewhere, right? Just to make it tractable. Otherwise, it wouldn't be a reasonable question. Yeah.
Are we ever going to need to do similar processes like this, but with different coordinate systems, in spherical?
That's a topic for next week. Yeah, we will get to such a thing, and there's a lot that needs to get said first. Yeah, but just as a foreshadowing thing, yeah, kind of. But yeah, it's different. Yeah. Okay, so once you know this, then you just look at your other equations and they kind of fill in the blanks. Y = 0 is this plane right there, which cuts through my prism to make this triangle. Right? And then the hard one, I suppose, is this one right here, which is, it's kind of angled, kind of like this, if you will. And that's going to cut through something kind of like that. And can't really do anything more with that. But it's over here on the right of the orange face, which is over there on the left. So here's our picture. And now we get to choose how we're gonna approach this. The first observation I'll make is that of your 6 choices, the only way to slice it, of those 6, that never slices through a corner is this one right here. dy dx dz. That's the only one that doesn't hit corners. And just as a, easy for example, if you were to, let's suppose you were to do your y slicing on the outside and say, well, my y slices look like this. What's the problem? Well, these y slices, as you move to the right, as y increases, everything looks fine until you get to here, where you find yourself slicing through a corner, which we don't want to do. When you slice through a corner, bad things happen. You're going to have to stop that integral there, start a whole new integral. Everything's going to be different, and it just makes everything harder. So bad news. And then etc. for your other slicing options. And I think it's a good, healthy exercise. Again, from a mathematical weightlifting point of view, think through all 5 of the other slicing options and persuade yourself that, yeah, sure enough, they're all going to slice through corners. They're all bad. Okay. All right. Here's the easier way to argue this, though, I think. And that is, there's a nice projection available. Specifically, if you look at the projection into the XZ plane, the projection is just a triangle. I like triangles. the upper bound surface. In other words, for a given value of x and z. For a given value of x and z, looking at that line segment, French fry, whatever you want to call it, the upper bound is a point that's always consistently on that one face, which has, of course, a consistent single equation. And then the lower bound for y, always on this face, which, of course, has a consistent, very convenient single formula. So this is, again, a good projection. The projection itself gives you your x and z bounds. Said differently, whichever plane you're projecting into must be your outside two differentials, and the projection gives you your outside two sets of bounds. And then the lower and upper come from these orange and purple surfaces respectively. And again, just solving for y, for the lower bound and for the upper bound. Everybody good? Okay. All right. This last example, I'm going to ask you all to read this last example. It is very, very similar to the example that we just did, just kind of different shapes. What you'll find amusing about this example is how weird the solid is itself. The solid is like, I've yet to really figure out a good real world relatable, like what is this thing? In some sense I'm imagining like a little goblet with a round bottom that's been turned on its side. I don't know. But very weird solid, but notice the projection into the XZ plane is very nice. And so we put X and Z on the outside. Think about our Y bounds by looking at the lower surface and the upper surface, and life ends up being pretty good. Details for y'all to take a look at. Okay, y'all have a good day. See you later. Okay.